Hi. There we go.
Welcome to the last session of CPP. So the first talk is about the formalization of the Martingale convergence theorems, and Kexing Ying will be giving the talk.
Yes, thank you for the introduction. I'm Kexing Ying, and this entire project was joined with Rémy Degenne. So in this presentation, I will be presenting our formalization of the Martingale convergence theorems in the theorem for Berlin. Yes, so before moving on to the formal definitions itself, let us first gain some intuition for what a martingale is. So one characterizing theorem for martingales is the optional stopping theorem, or otherwise known as the fair game theorem, which states that if you have a sequence of random variables, xn, taking where n is a natural number, xn is a martingale if and only if for all suitable stopping times, we'll come back to what this means, t, we have that expectation of x at the time t is equal to the expectation of x at the initial time. So by stopping time here, I mean a random time, by which I mean a random variable taking value in the time index of xn, so in this case, natural numbers. And it's a stopping time means that the decision of this, the decision to stop, is only dependent on the information that we have so far, so we cannot see into the future. There's numerous sufficient conditions for suitability here, and one simple condition is boundedness. So intuitively speaking, one way we can think about this theorem is that for a martingale, nothing can be gained by stopping this process based on the given information. Let us see a real-world example. So suppose we want to model the net worth of a player who is playing in a fair coin game. So in particular, this game involves the player guessing the outcome of a fair coin flip, and if they guess correctly, they double their money, and if they guess wrong, they lose their money. And at each round, this player bets one coin. So we can model this mathematically by taking a sequence of IID random variables xn such that xn takes 1 and minus 1 with probability 1/2, and then we define the net worth as xn, where x0 is defined to be 0, and for OK we define xk to be the sum. So this is the amount of money that this player have won after the kth round. One can show that xn is a martingale, and the game is always fair, clearly. So you cannot gain any advantage using the information that you have so far based on the previous coin flips. So taking xn as before, a famous problem that we can solve using the optional stopping time is known as gambler's rule. So intuitively speaking, suppose we have a player who is going bankrupt at, say, -8 net worth, and they will quit at, say, B net worth. We want to find the probability that this player goes bankrupt. So to find this probability, we introduce the following notation. So for each C, we define TC to be the first time for which the net worth is C. And then we want precisely P, the probability that P minus A is less than TB. To find such P, we introduce the following random time. So T is the minimum of T minus A and TB. Then by the law of total probability, as at time T, either the net worth has reached minus A or it has reached B, we have the following expression. And simply rewriting it, we have the expectation at time T is minus A times P plus B times 1 minus P. However, you can show that this is in fact a stopping time and is suitable. So therefore, by the optional stopping theorem, we have the expectation of xt is equal to its initial value, which is 0. Combining the two, we get a very easy proof what P is. So the motivation for this formalization stems from many different sources. So for example, well, obviously, martingales are a fundamental object in stochastic analysis. So they are applied everywhere, and a field is dedicated to studying them. On the other hand, they can be also applied in many places outside of probability. So in particular, there are many famous examples of probabilistic proofs using martingales of non-probability problems. So famous examples include the fundamental theorem of algebra, the compactness of the space of graphons, which is a combinatorial theorem, and the Weierstrass approximation theorem, and more recently, a breakthrough was achieved in the KLS conjecture using stochastic localization, which is a Martingale-esque kernel. Finally, it has many applications in finance, modeling, machine learning, and etc. So let us briefly talk about the history of formalization of probability theorem in different theorem provers. So most notably, previous works formalizing probability theory were done in Isabelle by Hisso Abigail and many others. So they have formalized parts of measure theory and characteristic function, and consequently the central limit theorem. They have also formalized the definition of conditional expectation using the Rhoda-Nikodym theorem, which contrasts to our construction, as I will show you later on. They have also defined Markov processes and kernels, and many other definitions. Degenne defined some of the prerequisites for probability theory in 2021. And most notably, he defined LP spaces and independence. Well, obviously, we had already defined some measure theory in mathlib, Ling's math library, including the definition of integration, stuff like that. The almost everywhere Martingale convergence theorem is one theorem that was also formalized in this project, one of the two major theorems. And this was first formalized by Vaja et al. In 2022 in COP. However, in contrast to their project, this project establishes a more general framework. So in particular, we defined martingales, which takes value in general Banach spaces. And this is useful, for example, if we want to formalize UMD spaces. We also, in our entire project, only required finite measures, in contrast to Vaja's, which initially decided on probability measures. So as mentioned previously, this entire project is formalized using the Ling theorem prover. Furthermore, this project has been contributed into mathlib, so subsequent works can be built on top of this one, and everything will function nicely. And as we shall see, we use a lot of existing theory that already exists in mathlib. So now let us get to the formal definitions. So conditional expectation is a very important definition for us for the definition of martingales, and it is written here as a proposition, but as we shall see, it is also a construction. So given X a random variable and G a subsigma algebra of F, a random variable Y is said to be the conditional expectation of X with respect to G if firstly Y is G measurable, and secondly, for all G measurable set S, we have this equality. So in particular, on the sigma algebra G, you cannot distinguish X and Y, yet Y is G measurable, so Y behaves nicely with G. Here we have a proposition of how conditional expectation should behave, but it turns out that the conditional expectation always exists and is unique if X is integrable. And we introduce this more probabilistic notation for Y. So intuitively thinking, we can think about sigma algebras as information. So we're restricting on to given some information, we restrict our possible events onto a smaller subset. So there's only smaller amount of possible events that can happen. And then, given our random variable restricted onto this small sigma algebra, we obtain a conditional expectation. For a process, this can be thought of as where we take a sequence of increasing sigma algebras. We can think about this as the information gained as the process progresses, and we condition on that subsequently. So let us look at the construction that we that's needed for conditional expectation. As previously mentioned, the definition in Isabelle uses the Rödel-Nikodym theorem. However, we decided, even though the Rödel-Nikodym theorem is proved in mathlib, we decided not to use it as it restricts us to the real numbers, or in particular, or more generally, any space that has the Rödel-Nikodym property. So this is not general enough for our purpose, as we want to define our Martingales for any Banach space valued random variables. So instead, we constructed the conditional expectation as using orthogonal projection. And this is done in 4 steps. So firstly, on L2, the L2 space can be thought of as the Hilbert space, and therefore it makes sense to do an orthogonal projection. So in particular, we're projecting from the larger L2 space onto the smaller restricted L2 space with respect to the smaller sigma algebra. Then you can approximate any integrable L1 functions by integrator functions. And finally, we define the general conditional expectation, a returning jump whenever it is not well-defined. We note that step 2 and 3 is similar to the construction of the Bach integral, where we approximate functions via simple functions. As a result, we were able to reuse a large part of or not reuse, but we were able to factor out large parts of the definition for Bach integration into its own separate construction, and such that we can reuse this construction for both the Bach integral and the definition of the conditional expectation. So in Ying, the definition has this type signature. As you can see here, we only require a complete normed space or a Banach space. And it applies for any random variables. And we don't require any conditions on the measure mu, where we return jump value whenever mu doesn't have the required so sigma finiteness is the required condition. Now we can talk about the definition of martingales. So a martingale is defined as this. So you take a increasing sequence of sub-sigma algebras, Fn, and Xn to be a sequence of random variables. Then we say Xn is a martingale with respect to this Fn, if firstly that Xn is integrable for any n, and it is measurable with respect to Fn for each n. So this is what this notation is saying. And secondly, for any m greater or equal to n, we have the conditional expectation of xm given Fn, and that equals Xn. So you might think about this as Fn is the information that we have after the n step, and your condition taking the conditional expectation of subsequent random variables on the current information. So the last condition is precisely saying that subsequent random variables given the current information is precisely the current random variable. So you cannot gain any additional information other than what we have so far. In the case that we replace the equality in the last condition with less equal or greater equal, we get the definition of super and sub-martingales. So this is the definition in Ying, and we know in particular that we do not require integrability, since by our construction, any conditional expectation is integrable. So as a result, the second condition here provides integrability. And the optional stopping theorem can be formalized as the following. However, we formalized it for sub-martingale, since this martingale version is a simple corollary, by noting that the martingale is both the sub and the super martingale. Where we take the negative of a sub-martingale, we get the super martingale. So we proved it for sub-martingale. And finally, we come to the main results of this project, which was the Martingale convergence theorems. So the Martingale convergence theorems is actually 2 theorems. So the almost everywhere convergence and the L1 convergence theorem. And there are many different sections to it. So in particular, the L1 convergence theorem has 3 different parts, while the almost everywhere convergence has 2 parts, I believe. Anyway, here I have a more simple version. So in particular, it says that if you have a sub-martingale, then if it is uniformly bounded, then it converges almost everywhere. And on the other hand, if it's uniformly integrable, then it converges in L1. So these theorems have many immediate corollaries. So in particular, as mentioned previously, in fact, the Martingale convergence theorem implied the Rother-Nikodym theorem. It can also be used to prove the strong law of large numbers, Kolmogorov 0-1 law, and the second Borel-Cantelli lemma. We note that the first three lemmas, theorems already exist in mathlib and were proved via different proofs. While the second Borel-Cantelli lemma is a specialization of the Lévy's generalized Borel-Cantelli lemma, which is proved as a part of this project. And we also proved the second Borel-Cantelli lemma as a result. So let me quickly give a brief proof outline. So the fundamental idea behind this proof leverages on the Doob subcrossing estimate, which states the following. So if you have a sub-Martingale and you pick 2 points A, B, and some natural number n, then we have the following expression where we have which takes expectation over what this un thing is. So what is un? So un is the number of upcrossings of the process x across the band AB before time n. So I have here an example of such a process xn. And what un is saying is we count before the number n. So here we have 13, I believe, 13 points. And before n, let's say 13, we count the number of times the process go from below A to above B. And this will be the un. So this is a random variable. And we can take that expectation of this random variable, and we have this bound, where this plus means the positive part of this random variable. So it leverages on this lemma, and since un obviously increases with n, we can take n to infinity, allowing u to be infinity if it's unbounded. Then we note that since the expectation at the right-hand side is finite due to boundedness in L1, the left-hand side is also finite. So therefore, we have the random variable u is finite almost everywhere. Namely that for any realization, it has finitely many upcrossings for any bands with probability 1. Then the almost everywhere Martingale convergence theorem follows straight away by noting that a real sequence converges if and only if for any AB in the rational numbers, the number of upcrossings of this sequence is finite. So if it doesn't if it converges, then it must either fall within the band or fall outside the band. So that's what this lemma is saying. And as a result, we have the convergence almost surely. So this project resulted in the formalization of many results, most of which I talked about already. We also, as a part of the formalization for the L1 Martingale convergence theorem, we also formalized the theory of uniform integrability. And as the consequence of the convergence theorems, we formalized many corollaries, including the Lévy's upwards theorem and the one-sided Martingale bound, and mentioned previously Lévy's generalized Borel-Cantelli lemma. So as a final remark, we note that the monolithic nature of mathlib was vital to this formalization. So as mentioned previously, we've utilized large parts of existing theory. So in particular, measure theory. We've refactored out the construction for Bach integral and used it for the conditional expectation. We used a lot of topology. We used the theory of conditional expectation, not conditional, orthogonal projection. So we didn't need to prove the orthogonal projection exists and is unique in particular. We also required to use lattice theory and many other things. We also noted some implementation issues regarding probability theory. And due to time constraints, I will not go into detail here, but you can find it in my paper. And as a result of this project, and as everything is formalized and committed to mathlib, this opens up a lot of doors for further formalization of probability theory. So for example, the second author, Degenne, and I have been working towards formalizing Markov kernels and disintegration theory. And of course, many other results can be formalized due to this project. Thank you for your attention.
Thank you for the talk. We have time for one question, maybe. If not, then I'll have to ask the question. So could you tell us whether your formalization diverged from either the previous formalization in Coq of the simplified setting, or of the paper arguments?
Yes, of course. So first, the L1 convergence theorem is not formalized in any theorem. So half of the results here are original, not formalized in any system. Secondly, the proof of Doob's the final part. So I lied a bit here. We didn't precisely use this second lemma in our formalization. So this is the proof that is normally used on paper. However, due to so a previous formalization of the Lebesgue differentiation theorem used a similar argument, which required different notion of upcrossings. So we were able to essentially use that lemma using a more complicated argument. However, saving us a lot of code duplication because we were able to use that argument.
Okay, thank you.
Thank you.